So, geometrical groups. When you're not given specific vectors, you can still use addition, subtraction. We have 3 vectors in working with things. And we can create and solve some geometrical problems this way without being fixed to like figuring things out on a regular Cartesian grid and figuring out that. Okay. So now, it's like I said before, you have a robot that can only go in this green direction M and this blue direction N, either forwards or backwards. And you have a problem. Your robot is at M, and you want it to get to N, right? And in our mind is like, go this way. But the robot's like, no, I can only go in green and blue directions. So you're like, your brain, our human brain says, oh, well then you can't do that. But the robot brain says, well, yes, I can, because if I'm at M, I can go back to O, and then once I get to O, I can go to N. I'll still get where you want me to go, just not directly. Okay, it spells the word moon. Anyways. So you go minus M plus N. So you just sort of draw the picture, map it out. I want to go from M to O and O to N. And then you write the vectors that way. Similarly, if you wanted to go from N to M, we could go NO and OM. Or we could just take our previous answer and put a negative in front of it and write M minus N. Now technically, when I write M minus N, technically that would be saying I'm starting at M and I'm doing this first. That's M. And minus N would be the same one backwards. So I'll take that red one and I'll slide it up there. Oh, perfect. I got to M. So we can rearrange things here, but that's technically what's happening. When I write M minus N, it's not following on our graph anymore. I started N, I went M, subtracted. So often I think I like to use the pictures and the lines that I have. So that's why I would write minus N first. I wrote minus N first and then plus M second. I can see it on the lines that were given. But writing it the other way still gets you to the same spot. Now, you're at the origin. Your robot only travels in direction M and direction N. And you want it to start at O and get to P. How would you do that? Okay. Well, if P is the midpoint, what I could do here is I could start at O, and I could go to M, and then I could go halfway from M to N, because P is halfway. So I write that out as the idea. Well, O to M, I already know that that's M. A little arrow over top. And M to N, I already figured out as well from part A, is minus M plus N. Yeah, if we were to write a test and I forgot those arrowheads, I'd have to take off half a mark for myself, because they need to be shown as vectors. And technically here they're bolded, which is officially okay for vectors, but I like the arrowheads better. Just really. And then here you can just do mental math, like regular algebra. Keep adding my arrowheads. And according to this, I could get from O to P if I went half of M and half of N. So I'm going to just draw, to the best of my abilities, half of M, and I'm going to draw, to the best of my abilities, half of N. I think those arrowheads pretty good. And if I went that and I added this one to there, oh, look at that, I'm right at P. And I'd tell the robot to do that, then turn and do the other one, and it would get from O to P. This would be disastrous, though, I think, if we had cars that only could go in two directions. You could get anywhere you wanted to go eventually, but it just wouldn't work very well. Or you just do little bits of each one, so you'd be like shaking around like that as you would go. Oh, now we have a more sophisticated robot. Our more sophisticated robot can go in 3 different directions, A, B, and C. And first of all, we want it to go from A to P, and from O to P and O to Q. Find those position vectors where P and Q are midpoints. So we think a pathway that we could do. I could go from O to P if I went O to A and halfway between A and B. And then I think, well, O to A is just the vector A. And A to B would be going A back to O and then to B, so it would be negative A plus B. Distribute my half, add my like terms together, and just like we found with the midpoint, with the m's and the n's, we get halfway to A plus halfway to B, right? So I take half of A here in blue, and half of B here in red. Technically, if I added them together, well, look at that. I get nicely to P. So now I've got O to P. And similarly, I could do the same thing with O to Q. I could go halfway to B plus halfway to C and get from O to Q. But then this allows us to say, all right, you have a robot that's starting at point P, we want it to get to point Q, and we're only allowed to travel in A, B's, and C's. How should we do that? Well, since I already know the green dotted line and the blue dotted line, I figured that out in A. Can you see how nicely we go back to O, and then go from O to Q? That's free vectors. So PQ would be PO plus OQ. And then we already know what those are, and we put them together, and apparently we get negative half A plus half C. The B's go away. I'm terribly curious, if I put this together, here's half of A, but negative direction would be this way. And then half of C would be this. And if I started at P, and went negative half A, and then went, oh my goodness, that's cool. It works out perfectly. Okay? Now, what we just discovered with our math here was probably the most efficient way to tell your robot to go from P to Q, using what you have. Can you see without the vectors, you'd be sort of scrambling, like, I don't know. Like if you just had toggles where you could move you'd probably be moving your robot be like going all over the place, and then you'd eventually back it up a little forward, then back it up forward, and you'd get it from P to Q. But this would be the most efficient way. And I guess if we could break up P into little pieces, 10 little pieces, and Q into 10 little pieces, and then do one little red and one little. It would still take the same amount of time, but it would seem like it was going more along the straight path that we would like it to. Okay. Remember, vectors are free. We can have O as the origin and fix it there, but we can also think of vectors being free in this situation. So we've got two vectors, the vector A right here, and the vector B right there. And we want to find the following. How could I go from O to B if my robot could only go in directions A and B? Well, I would tell my robot to just do A, O to A, and A to B. Just do A plus B. But now I want to go from B to D with my robot. What could I do? Can you find a pathway that starts you on here using what you know and gets you to D? And there's a lot of different routes you could take. I decided to go from B to A and then go A to O twice. You could also go B to C and C to D. And since C to D, we'll just draw C to D in red. Can you see that C to D in red is exactly the same as B to O was? So doing that math, we could go, to get from B to D, we could go negative B and then minus 2 A's. I guess here we have to know a few things about hexagons. Because it does tell us it's a hexagon and it's a regular hexagon. Did you know a regular hexagon is made up of a whole bunch of equilateral triangles? And each of them have the same length. And so my A to B vector, because these are all, is equal to my C to O vector. And since vectors are free, this is just going to be negative 2b. So if I took two of those, one there and then another one there, that would get me all the way across. You need to go back to part one. so we've got some interesting things happening in this diagram. First of all, they're telling us A and B. They're wanting everything in terms of A and B, so this is the only direction your robot can go. In directions A and B for as long or as short as you want, either forwards or backwards. Okay? And they give us some other things like the ratio from AB to BP is 2 to 1. And the ratio from CQ to QB is 1 to 3. So we're going to have to use those ratios involved in this as well for telling our robot how far to go in which direction. First of all, if you wanted to go from A to B, that looks really simple for telling my robot. I just say, hey robot, go back to O. So go A to O and then O to B, so that'll be negative A plus B. My robot would make it there, no problem. But if I wanted to go from A to P now, I've got that ratio in place that AB to DP is 2 to 1, which means that this is 2 of a unit, that's 1 of a unit. I don't know what it could be. It could be 8 and 4, it could be 6 and 3, I don't know exactly, but the ratio 2 to 1 tells us A to B is twice as long as B to P. So we somehow have to use that to figure out A to P. Does this make sense? If I went from A to B, and then I did another half A to B, because the ratio of BP to AB is half of that, I would get all the way there. So this becomes 3 halves AB. Which we know what those numbers are already, we can plug them in. Negative 3 halves A plus 3 halves B. I'm going to write this ratio CQ 1 to 3. See, these aren't lengths, right? When I write them in, they're not lengths because obviously A to B and C to B, this is a parallelogram. I don't know if it's an equal parallelogram, but my 3 looks shorter than my 2. So they're not actual lengths, they're just proportions, right? If I write it this way, does it make sense that C to Q is 1/4 of the way? Not 1/3, it's 1/4 of the way from C to B. So sometimes writing those numbers can help us see some of those proportions. Okay? So we want to figure out O to P. Well, I just figured out I can go from O to B and then add B to P. And B to P was 1/2 A to B, which I already figured out. So the quickest way is to do 3 1/2 of B minus 1/2 of A. I want to draw it out, but I think it'll actually go off my screen and then I'll be bothered. You won't believe me because it'll be in the black part. But can you visualize it? Can you take 1 1/2 of these and then go back along A? Seems reasonable that we would get from O to P. O to Q. We would want to go from O to C to Q. That's really easy to visualize. And C to Q is 1/4 of the way from C to B. And O to C, since it's a parallelogram, is the same as A to B. So I can just do this switch in my work, even though it's not fixed anymore, but those two vectors are free. So whatever O to C is was the same instructions you would tell your robot to go from A to B. And we already know A to B, and C to B is the same as O to A. So we do some weird switching here, but it makes us substitute into our vectors even faster. And it says if you went 3/4 of A plus B you would get from O negative 3/4 of A. So I'm going to estimate that's negative 3/4 A. And this is B. See how good my estimate was. If I start at O and go this, and then I go this. So it's so exciting when it ends up where you kind of want it to be. Then you can I kind of cheat because I make it seem like it's perfect when it's just off a little bit. That's so cool. So again, vectors, I hope this robot analogy is helpful for you because sometimes people are like, why would I want to do that? Well, these are the restrictions you have. You have O and A and B, and now what do we finish with here? We can find Q to P. We can tell our robot to go from here to here. How are we going to do that? 1/4 of A, I'm going to draw a 1/4 of A, and half of B. Let's see how that works. If we start with this one. It's close. I feel. And we get a result.